Greetings. I would like to take you through the presentation titled Designing a Deep Learning Neural Network for an Acousto-Ultrasonic Investigation on the Corrosion Behavior of Cotton Steel. I'm Vimalathithan, and this is my research group, Claudia, Barile, Caterina, Casavola, and Giovanni, Pappalettera. We are from the Department of Mechanics, Mathematics and Management of Politecnico University of Bari. This is the summary of my presentation. First, I will introduce you to the basics of acousto-ultrasonics and cotton steel, followed by the materials and the test setup that we used, and then the objectives of this research work. This will be followed by the characteristic features of the acoustic waves studied using wheel packet transform, Mill spectrograms, and fast Fourier transform. And then I will introduce you to the architecture of the deep neural network that we designed for the study, and then the accuracy of the CNN that we have trained. Finally, the conclusion. First, acousto-ultrasonics. It is a method in which artificial stress waves or acoustic waves are simulated through a material and allow it to propagate for a predefined distance before being recorded by a piezoelectric transducer. The characteristic features of the propagated waves can describe the properties of the medium in which they are propagating between their source and the receiver. This is due to the reason that there will be an energy loss during the wave propagation and also an attenuation in terms of amplitude and frequency due to the geometrical configuration and the material properties of the propagating medium. For example, when an acoustic wave is allowed to propagate through a narrow geometrical boundary, there will be lots of reverberations. These reverberations can attenuate the signal in terms of both amplitude and frequency. Besides, the variation in surface roughness and also in internal properties such as Young's modulus can attenuate the amplitude and frequency. Therefore, by analyzing these waves in their time frequency domain, the properties of the propagating medium can quantitatively be characterized. Next, cotton steel, or as you may know it as a weathering steel, which can be oxidized on the surface to form a stable rust-like appearance without diminishing its integrity. So we can say that there will be an obvious difference in surface roughness between a cotton steel which is exposed to the oxidation and which is not exposed to the oxidation. These differences will affect the attenuation of the propagating waves in different ways, which can be studied using acousto-ultrasonics. So this forms the basic idea of this research work. In this study, we tested 3 specimens named A, B, and C, whose geometrical configurations were presented in the table. Specimens A and B were coated with an oxide activator and allowed the rust formation for 24 hours, while specimen C was tested under virgin conditions. The idea is to understand the attenuation difference between specimen A and B in terms of the difference in their thicknesses, while understanding the differences between specimen B and C in terms of the rust formation. For the acousto-ultrasonics, we generated the stress wave by a burst voltage of 28 volts and a width of 5 microseconds, allowing it to propagate through these specimens. The propagated waves were recorded by a piezoelectric general purpose sensor with an operating frequency of 150 to 400 kHz. The recorded signals were amplified by 40 decibels before being analyzed using PAC-PCI-2 data acquisition system. So the objective of this study is to simulate stress waves through these 3 different configurations of cotton steel specimens and analyzing these propagated acoustic waves using fast Fourier transform, wheel packet transform, and Mill spectrograms. And finally, to develop a deep learning neural network for classifying these propagated signals in these 3 different configurations of the specimens. The characteristics of the input signal is presented here. As I mentioned, the 28 volt burst voltage is used for simulating these stress waves, but the first structural response from the surface of the specimen is considered as the input signal. The FFT shows that the input signal has a frequency centered around 350 kHz, and when the signal was decomposed to level 3 using wave packet transform, it shows that 84% of the spectral energy is around 312.5 to 375 kHz frequency range. The FFTs, or the propagated signals, in specimens A, B, and C are presented here. Three observations can be made from these results. The first one is the obvious attenuation difference in terms of both amplitude and frequency between the input signal and the propagated signal in each of these specimens. The second observation is the attenuation in terms of frequency, particularly around 120 kHz between the signals from specimens A and B. As you may recall, both specimens A and B were coated with an oxide activator and rust was formed on their surfaces. The only difference between specimen A and B is their thicknesses. But this difference in thickness was responsible for the attenuation of the signal in terms of the frequency. The last observation is the attenuation in terms of amplitude between the signals from specimens B and C. Once again, as you may recall, specimens B and C were similar in terms of their geometrical configuration, but the only difference is that specimen B was coated with the oxide activator and allowed the rust formation, but specimen C was tested under virgin conditions. But this difference leads to attenuation in terms of their amplitude. So this shows that there is an obvious attenuation difference which can be exploited to understand the characteristic features of these specimens. The percentage of spectral energy calculated using Euler packet transform for each of these signals also shows the attenuation differences in terms of frequency. But why did we go for MEL spectrograms while we could have presented these results in terms of the histograms of the Euler packet transform? Because we wanted to use these waveforms as an input for training our deep neural network models. There are two reasons behind it. The first reason is that MEL spectrograms are most commonly used input forms for training a neural network model. The second reason is that when these acoustic waves were rescaled into their MEL frequency and presented as MEL spectrograms, they show more distinct features which enables the neural network model to learn more efficiently. This is better than feeding the continuous Euler transform or fast Fourier transform or simply time series data as the input. This is the architecture of the convolutional neural network that we developed for classifying the signals in the study. There are three convolutional layers. Each of them is followed by a pooling layer and a ReLU activation function. The stochastic gradient descent algorithm is used for training the model. There are three classes of signal in the study. The signals propagated through specimens A, B, and C respectively. 10,000 signals of each of this class, so a total of 30,000 signals, were used as a training data, while 15,000 signals were used as the testing data. The confusion matrix shows that the accuracy of the CNN model is more than 99%. Only one signal of class B is wrongly identified as class C. Other than that, the system works almost perfectly. You may wonder where this could be used in practical applications. Let's take this case. We have two carbon steel structures, one having rust formed completely and stabilized, another one without any rust formation. So we will know the propagation of acoustic waves and their characteristics in terms of time and frequency domain. And we could use these features while analyzing a carbon steel structure which is exposed to the corrosion environment. So we will know exactly at what time the structure has stabilized after the rust formation by analyzing these acoustic emission waveforms. And this can be done automatically by feeding these data as an input to the computational neural network. So this is one of the applications where it can be used, but the application is more wider than we might think. I would like to conclude this presentation by highlighting what we have done so far. The acoustic wave attenuation due to the thickness and the surface of the carbon steel were investigated. These results will help in identifying the stability of the corrosion formation on the surfaces of the carbon steel specimens. The deep learning neural network will come in handy when identifying the transition between the rust formation automatically by analyzing these acoustic signals. Unfortunately, at this moment, no morphological results of the rust formation and the other properties about the carbon steel or the oxide activator could be provided. But if you have any questions regarding the methodology that we have used, please feel free to contact us. And thank you for your attention. This is Vimalathithan.